Hello everyone. In this video, I'm continuing my experiments with dinitrophenyl oxalate and peroxyoxalate chemiluminescence, or simply the glow stick reaction. If you're not familiar with what I'm talking about, please watch my previous video on dinitrophenyl oxalate. In the last video, I explained the reaction mechanism and mentioned that the color of the light emitted depends entirely on the dye used. Typically, polyarene fluorescent dyes are used in this reaction, and here are their structures. These dyes are very expensive and I don't have them. With the dyes I do have, I was only able to achieve yellow and red colors. Yellow came from rhodamine 6G and red from rhodamine B. However, I want to achieve a green or blue color. Commercial glow sticks use diphenylanthracene for this purpose, but as I said, I don't have it. And then it occurred to me, theoretically, anything that fluoresces should glow in this reaction. This means it might not just be fluorescent dyes. For example, quantum dots could also work, as they fluoresce quite well. So I decided to do a quick experiment. Synthesize the simplest carbon quantum dots and see if they would glow in the peroxyoxalate reaction. The simplest homemade way to obtain quantum dots is to bake a solution of urea and citric acid in a microwave oven. So, that's what I did. I took 1 gram of urea, 0.5 grams of citric acid, added a little water, and put it in the microwave. When the water evaporated and the mixture turned brown, I removed it from the heat. At first glance, nothing interesting happened. The mixture simply resinified. But if you take a little of the mixture and put it in water, it starts to fluoresce strongly green, which means the quantum dots were successfully synthesized. I added a little water to this mixture to create a concentrated solution of quantum dots. Now it's time to see if they'll glow in the peroxyoxalate reaction. I took some of this concentrated quantum dot solution and added it to a vial, then added acetonitrile to dissolve it. To this solution, I added a small amount of dinitrophenyl oxalate. I turned off the light and added a few drops of 60% hydrogen peroxide, and the reaction glowed with a blue-green light. Unfortunately, the glow was quite weak and didn't last long, nowhere near as bright as with a dye. It could be compared to the luminescence of lophine, but it was there. And the fact that such a quick and dirty experiment even yielded a result is a miracle. In theory, it simply shouldn't have worked. The thing is, I synthesized hydrophilic quantum dots. They dissolve and fluoresce very well in water, but peroxyoxalate chemiluminescence occurs under anhydrous conditions. Therefore, these quantum dots are not suitable for this reaction, which is why the glow was very weak and short-lived. In general, quantum dots can glow very brightly in this reaction, but for this to happen, they must be highly soluble in organic solvents, fluoresce in organic solvents, be purified from synthesis byproducts that can quench fluorescence and have high fluorescence efficiency. Synthesizing such quantum dots is a complex task. It's much simpler to achieve these same results using appropriate fluorescent dyes, which is the main reason why commercial glow sticks use classical fluorescent dyes rather than quantum dots. Nevertheless, I'll continue to experiment in this direction. At the very least, I'll try to purify my quantum dots. If anything comes of it, I'll share it with you. That's all for today. Goodbye.